Hopefully you feel comfortable with Boyle's law, P1 V1 equals P2 V2, and Charles's law, where V1 over T1 equals V2 over T2. Now, in this section, we are looking at the relationship between temperature and pressure, which is Gay-Lussac's law. You'll be able to calculate the unknown temperature or pressure when the volume and the amount of gas does not change. Gay-Lussac's law states that the pressure of a gas is directly related to its temperature when volume and amount of gas is constant. So if the pressure increases, then the temperature increases. Just like Charles's law, when one increases, the other increases, or if one decreases, the other decreases. Let's look at their example. My original temperature here was 200 Kelvin. When I double the temperature, notice I add a ton of heat to 400 Kelvin, my pressure went from 1 atmosphere to 2 atmosphere. Notice that my volume stayed the same. So within this container, with the volume not changing, the pressure doubled when my temperature doubled. We can show this again in a fraction form, and we say that there is a direct relationship between pressure and temperature. Again, all temperatures need to be in Kelvin. Let's look at a sample problem. Home oxygen tanks can be dangerous if they are heated because they can explode. An oxygen tank has a pressure of 120 atmospheres, I'm going to call that P1, at a room temperature of 25 degrees Celsius. That's our T1. I'm going to add 273, so that's 298 Kelvin. If the temperature of the gas inside the oxygen tank reaches 402 degrees Celsius, so this would be a T2, let's add 273 to get to Kelvin, that would give us 675 Kelvin. What will be its pressure in atmospheres? And because we started our pressure in ATMs, we can finish in ATMs. It then goes on to tell us that the oxygen tank may rupture if the pressure inside exceeds 180 ATMs. So let's figure out what that pressure is, and if it's above 180, it would rupture. If it's less than that, it won't. Using Gay-Lussac's law, P1 over T1 equals P2 over T2, I put in my P1 over my T1 equals P2 over 675. I'm going to do my cross multiplying, so I will have P2 times 298 is equal to 120 times 675, which would give me 81,000. And to get P2 by itself, we'll divide both sides by 298. And my calculator tells me 271.8. Let's see how many significant figures we want to finish with. It looks like if I go back that we had 2 significant figures, 2, 3, so we want to end with 2. So I'm going to round that 271.8 to 270 ATMs. That would be our P2. Let's make sure that it is logical. If my initial pressure was 120, my temperature went from 298 to 675, so temperature increased. That means pressure must increase. And pressure went from 120 to 270. Yep, that definitely increased. This is 270. It wants to know, will that rupture? Well, it said that it could rupture if it was greater than 180. So yes, it definitely is at risk of blowing up that tank. Let's look at vapor pressure and boiling point. When liquid molecules with sufficient kinetic energy break free from that surface, they become gas particles or vapor. In an open container, all of the liquid will eventually evaporate. Think about it. Have you ever left a cup of water sitting on your counter and just watched it for days? It slowly goes away. In a closed container, the vapor accumulates and creates pressure called vapor pressure. Each liquid exerts its own vapor pressure at a given temperature, and as temperature increases, more vapor forms and vapor pressure increases. Vapor pressure is the pressure above a liquid at equilibrium in a closed container. At the boiling point, it becomes equal to external pressure. Vapor pressure in the bubble creates the atmospheric pressure. Let's look at this picture. We can see that our atmospheric pressure is 760 millimeters of mercury, and we're at boiling point here. And the vapor pressure that's in the bubbles at the boiling is 760 millimeters of mercury. It equals one another. The boiling point of water depends on the vapor pressure and is lower at lower temperatures. Look at this. The vapor pressure of water at 0 degrees Celsius, there's a vapor pressure of 5 millimeters of mercury. Compared to at 100 degrees Celsius, the vapor pressure is 760 millimeters of mercury. The boiling point of water depends on vapor pressure. It's higher at higher pressures. Let's look at the pressure when the boiling point, we just said at 100 it was 760, but let's look at 180. It's at 7,600. At a pressure of 7,600, the boiling point is substantially higher at 180 degrees. In a closed container, a pressure greater than 1 atm can be obtained, which means that water boils at a temperature that's higher than 100 degrees Celsius. Laboratories and hospitals used closed containers called autoclaves to sterilize lab and surgical equipment. Take a minute to look over this learning goal to make sure that you understand Gay-Lussac's law. We have looked at 3 individual gas laws. Boyle's law looks at pressure and volume. Charles's law looks at volume and temperature. Gay-Lussac's looks at pressure and temperature. Notice that each one of these is looking at pressure, volume, and temperature in one way or another. So let's use these 3 and let's combine them to calculate the unknown pressure, volume, or temperature of a gas when changes in 2 of these properties are given and the amount of gas does not change. So in each one of these, we're only looking at 2 variables, pressure and volume and temperature, pressure and temperature. Now let's look at all 3 of them together. The combined gas law incorporates all of them by smushing them all together. Notice that P1 V1 equals P2 V2. That's Boyle's law. And then V1 over T1 equals V2 over T2. That's Charles's law. And then the last one is P1 over T1 equals P2 over T2. That's Gay-Lussac's. So we just smushed all 3 laws together to make the combined gas law. This sums up each one of those laws, Boyle's, Charles, and Guy's, looking at the individual relationships for those laws and putting them all together for the combined gas law. Let's do a sample problem. We have a 25 milliliter bubble. That's a volume. It's released from a diver's air tank at a pressure of 4 atmospheres and a temperature of 11 degrees Celsius. Let's add 273. What is the volume in milliliters? Okay, so it's asking me to find V2 of the bubble when it reaches the ocean surface where the pressure is 1 atmosphere, so that's P2, and the temperature, T2, is 18 degrees Celsius, so 18 plus 273, which would be 291 Kelvin. The amount of gas does not change. So we know the initial volume, pressure, and temperature, and we know the pressure that it changed to and the temperature that it changed to. So we can solve for V2. Let's set it up using our combined gas law equation. P1 times V1 over T1. Well, our P1 is 4 atmospheres times our V1, which is 25 milliliters, divided by T1, which was 284 Kelvin. That's equal to P2, we know was 1 atmosphere, V2 is our question mark, and our T2 was 291. How do we go about solving for V2? I suggest doing the same cross multiplying that we did. We can still do all of these times each other. 4 times 25 times 291. That would give us 29,100. And then that will be equal to 284 times 1 times V2. 284 times 1 is 284. And then we leave the V2. There we go. Now we can divide both sides by 284 to get V2. My calculator gave me 102.46. I need to go back and look at significant figures, and there should be 3 everywhere, so I'm going to end with 3. That 4 will not change it. So my V2 would be 102 milliliters. Check your learning goal to make sure that you understand the combined gas law.